Hello everyone. Welcome to the third part of the Introduction to Verilog lesson series. Now in previous lesson we looked at the basic conventions or syntax that you can use in Verilog. Those syntax will help you in modeling a digital circuit with Verilog. Today we'll look at a key concept, one of the key concepts that is helpful when designing digital circuits in general. So this concept is called hierarchical modeling, and this will be really helpful when you are designing circuits with Verilog as well. So the content that we cover in this lesson is related to the chapter 2 in the reference book. So if you want to get more information or more knowledge, additional knowledge, you can read the chapter 2 of Verilog HDL reference book. Now, the concept of hierarchical modeling can be best explained with an example. So here you can see a high-level view of a 4-bit triple carry adder, and I guess you all have already seen and looked at the behavior and internal construction of an adder in the 221 course. Anyway, we'll be going through the construction of a 4-bit adder to understand the importance and the usage of hierarchical modeling in digital circuit designing. So if you look at the diagram, here we have two 4-bit inputs A and B, and also there's a carry in coming into the adder as an input. The addition of A and B are taken from the output S, which is also 4 bits in size. And also there's a carry out output, which is used to get the carry out from the addition, if there's any. Now we can see how hierarchical modeling can be used to build this 4-bit full adder. Now hierarchical modeling basically is about having a hierarchy of design elements to simplify the process of building a larger complex circuit. Here you can see the 4-bit full adder. We have broken it into 4 1-bit full adders, and when these 4 1-bit full adders are connected as it's given in the block diagram on the slide, you can achieve a 4-bit full adder. So you can study the diagram given here and you will understand that it builds a 4-bit full adder. Now the corresponding bits from the 4-bit inputs A and B are connected to the 1-bit full adders. For example, A0, B0 are the least significant bits of A and B inputs respectively, and C0 is the carry in for the 4-bit full adder we saw in the previous slide, and C1, for example, is the carry out of the rightmost full adder, and in the result or the addition result, S0 is the least significant bit of the addition result. And I hope you can get the idea and understand how other inputs and outputs work here. So it's quite simple. So this is how you can break a 4-bit full adder into 4 1-bit full adders. And here it shows how the 1-bit full adder we saw in the previous diagram can be constructed using 2 half adders. So I think half adders also you already have seen in the course. So a single 1-bit full adder in the previous diagram we saw can be implemented or replaced with this diagram for the full adder. Now here we go to the deepest level in the hierarchy, where we construct the half adder in the previous diagram using basic logic gates. When you implement the half adders in the previous diagram using these basic logic gates, you get the full 4-bit full ladder in terms of basic logic gates. Uh, so and now in this slide, you can see the whole process we went through to design the 4-bit full ladder. The top level design was first broken into 1-bit full ladders, and then those 1-bit full ladders were broken into half adders, and finally the half adders were implemented using basic logic gates XOR and AND. Now this whole process we looked at is called hierarchical modeling, since it breaks a larger complex circuit into a hierarchy of smaller components. So with this, the overall design procedure uh, become easier compared to designing the full circuit using basic gates at once in one go. Now we have looked at what hierarchical modeling is by using an example design. Now here we can discuss about two main design methodologies that make use of hierarchical modeling we talked about. The two design methodologies are top-down design methodology and bottom-up methodology. In top-down design methodology, we define the top-level block and identify the sub-blocks necessary to build the top-level block. Now we do the same for the sub-blocks as well. We continue doing this until we come to leaf cells which cannot be further divided. Actually, the example about 4-bit full ladder we looked at earlier is an example for this top-down design methodology. There we started from the top level design and went on breaking it into sub-blocks until we came to basic logic gates. The second design methodology is bottom-up design methodology. Here we first identify the basic building blocks that are available to us, and we build bigger blocks using these basic building blocks. The bigger blocks are then used for higher level blocks until we build the top level block that we need to design. Here it shows an abstract view of how top-down design methodology works. You start from the top level block and start dividing it into sub-blocks until you get to the leaf cells which cannot be further divided. Here it shows how bottom-up methodology works. You start with leaf cells that are available to you and start combining them into larger blocks. We continue doing this until we get to the top level design that we need to build. Now that we have looked at the main two extreme design methodologies, we can look at the design strategy which is typically used in the industry. The typical strategy is to use a combination of both top-down and bottom-up approaches we talked about earlier. And this is known as hybrid method. The design architects usually define the high-level specification of the top-level design block, and the logic designers break this top-level block into sub-blocks, as we discussed in the top-down approach. And at the same time, the circuit designers start building optimized circuits for the leaf cells. They also start building higher level cells by combining these leaf cells. So these two processes meet at an intermediate point. The low-level circuit designers end up creating a library of leaf cells using switching elements in electronics, things such as transistors. And logic designers end up designing a top-down hierarchy until all modules are defined in terms of these leaf cells. So the two processes, top-down and bottom-up, meet at this point. Now, this process is known as hybrid method, and it is typically practiced in the digital circuit designing industry. So now we have looked at what hierarchical modeling is and different strategies that make use of it. As we already saw, hierarchical modeling basically is about having a hierarchy of design elements to build up a single top-level circuit. Now we'll see how hierarchical modeling is facilitated by Verilog. This is facilitated mainly by the concept of a module in Verilog. A module in Verilog is a basic building block or a circuit element designed to perform a certain task. And a module can be a collection of lower level submodules. We'll talk more about modules in coming slides. And as it was mentioned in the previous slide as well, elements or submodules are grouped into modules to provide common functionality that is used at one or many places in the circuit design. And when you use a pre-implemented module inside a larger circuit, you hide the internal implementation of that module. The functionality to the higher level block or the larger circuit is provided through something called the port interface of the module. The port interface basically is the inputs and outputs of that particular module. You will understand how modules work better when we go into a real example, which will be discussed soon. Now, with this module concept in Verilog, you can modify the internal implementation of a particular module without affecting the rest of the design, given that you don't change the port interface of that particular module. Now, for example, you might get the need of optimizing the internal implementation of a particular module, a module such as an adder, at a later stage in design process, and you can easily do this with this modules concept in Verilog. Okay, so now that we got some idea about what modules in Verilog are and how they could help us do hierarchical modeling, we now can look at how a module can be defined in Verilog. Here we'll be just looking at the basic structure of a module only. More fine details about Verilog modules will be discussed in the next lesson. So a module can be defined with the keyword module. Immediately after the module keyword, you need to give the name to be used for the module, a unique name to be used for the module. And then you can specify the module terminals list. The terminals list of a module is basically the port interface we talked about earlier. In simpler terms, this basically is the inputs and outputs list of the module. You will understand this better when we go for a real example. Anyway, after the module name and the terminals list are specified, you come to the core of the module, where you define the internal structure of the module. This is where you will be writing HDL code to get the desired behavior of the module. If it is an adder, you will construct the behavior of the adder here. You will learn how you can do this at gate level in the coming lessons. And once you are done with specifying module internals, you should end the module with this end module keyword. So that's about how you can define a module in Verilog. And now here is an example module written in Verilog for a ripple carry adder. As you can see, it's of course an incomplete module. The key components of a module we discussed in the previous slide can be seen here. The module name has been given as ripple carry adder 4, and the terminals list include the A, B, C, in, S, and out. Out of these terminals, A and B are the main inputs for the adder. The input numbers that should get added, and C in is the carry in input. S is the sum output of the adder, and C out is the carry out output of the adder. Now, once the ports or terminals list is defined, you should write the functionality of the adder. Once this is done, you should close the module with end module keyword. So you will actually see how a complete module can be written in Verilog in coming lessons. And now we will be looking into something called instances in Verilog. This is actually heavily connected with modules concept in Verilog. The modules we have been discussing about so far act as a template from which you can create actual objects. In other words, when you create a unique object from a module template, we call it an instance. So if you are familiar with things such as object-oriented programming, uh, a module in Verilog is similar to a class in or object-oriented programming, and instance is similar to an object created from that particular class. So if you are not aware about all those object-oriented concept, you don't need to worry. We'll be looking at instances and modules and how they work here in these lessons. So you don't need to worry about previous knowledge. Now, anyway, each object or an instance has its own name, variables, parameters, IO interface, etc. This process of creating objects from a module template is called instantiation, and the created objects are called instances in Verilog. Again, you will understand this concept of instantiation and instances better when we create instances from modules in coming example designs. Here, you can see a completed example Verilog design for a 4-bit triple carry adder, right? So you can see how modules needed to build the adder are defined, and how hierarchical modeling is achieved using modules in Verilog. Also, with this example, you can see how instances work, instances and instantiation work. So here you can see the main ripple carry adder for module defined with its ports list A, B, C in, S, and C out. And at the beginning of the module internals, IO signals are declared. A, B, C in are declared as inputs, while C and C out are declared as outputs. More details about IO port declaration we will discuss about them in the next lesson actually. So this is just to give you an idea about how you can write a module in rough idea about how you can write a module in Verilog. Now next, you should notice that A, B, C here are buses with 4 wires in each of them. In other words, A, B, and C are 4 bits in size. And C in and C out, they are single bit wires. You can see that. So we have looked at these vectors in Verilog earlier. So A, B, and S are these multiple bit wires, and they are also called as buses. We already have looked at them. And then you can see to connect instances we have defined 3 wires. They are we call them internal wires. They have been named as Cout1, Cout2, and Cout3. Now at the beginning of this lesson we saw that a 4-bit adder can be implemented using 4 1-bit full adders. Here we are going to do this with Verilog by creating a separate module for the 1-bit full adder and using it multiple times in the main 4-bit adder module. You can see the implementation of 1-bit full adder defined as a separate module named full adder. So you can see it at the bottom right corner in the slide that has been defined as a separate module named full adder. The 1-bit full adder's behavior is written using behavioral modeling in Verilog. If you can remember, we talked about multiple modeling techniques in Verilog in the previous lesson. So you can do modeling with multiple multiple ways: behavioral modeling, gate level modeling, and data flow modeling. So here we have used behavioral modeling. But you can ignore the implementation details for now if it is not very clear, because we will not be looking at behavioral modeling in Verilog in this course. In this course, actually we will later look at how you can model or write code for a circuit like this using gate level modeling, right? So behavioral modeling, we'll not talk about it in this lesson, in this course. How you can define module internals using gate level modeling, we will talk about that in later lessons. Okay, so now that we have the 1-bit full adder module, we can instantiate it 4 times in the main 4-bit adder module to get the functionality we want. We are giving each 1-bit full adder a unique name. They have been named as, if you look at the code, you can see they have been named as FA0, FA1, FA2, and FA3. Also, an important thing you need to note is that just after the module name, uh, you, you have to give the give a unique name for the instantiated module as given in the example. So these FA0, FA1, FA2, those are unique names given to the instantiated full adder modules. You have to give that name just after the module name. This is how you actually do the instantiation. So you can notice how we applied the instantiation concept we discussed earlier inside our 4-bit adder module. Okay, so we are done with the instantiation of 4 1-bit full adders. And now we need to connect signals appropriately to these instantiated modules. For the 0th full adder module, or FA0, we are connecting the 0th bits of A and B signals so that they become the single bit inputs that should get added by the 1-bit full adder module, 0th 1-bit full adder module. The carry in coming to the big 4-bit full adder, which is the carry in coming from outside the ripple carry adder force. The main carry in input coming into the big ripple carry adder 4 module. We connect it to the carry in of FA0 full adder. And the 0th bit of sum S is connected to the sum of FA0, so that it will get assigned to the addition of A0 and B0. The carry out of 0th full adder is taken to C out one wire, which is an internal wire we defined earlier. Uh, uh, we take the carry out to that C out one wire by connecting it to the 0th full adders as the last signal or the last argument. So with this, I hope you can get the idea about how signals should be connected to an instantiated submodule properly. So you can see you have to connect the signals to the submodule properly in the same order as they are given in the submodule's definition. For example, here the 1-bit full adders definition you can see at the bottom right corner. So the signal order, the order of signals in the definition, they have been given as A, B, C in, S, and C out. So when you are connecting signals in the instantiated module, you have to give them in the same order as they are given in the submodule's definition. So these are important things you need to notice. And now that we are done with FA0, we can go and connect signals properly for FA1, which is the second 1-bit full adder. The signal connections to FA1 are very similar to that of FA0. You can see that here. There you can see we have connected the carry out of 0th full adder, which is C out 1, as the carry in for the first one bit full adder, that is FA1. So the carry out of FA0 is the carry in for the FA1. So we have already looked at the block diagram of this thing. So if you go back and look at it and compare this implementation with that, that is exactly what we are doing here. We connect the signals properly in Verilog. So you can do this with Verilog. And by repeating the same procedure for FA2 and FA3, we can successfully build the 4-bit triple carry adder. So there we used hierarchical modeling. Like you saw how you can use hierarchical modeling in practice in Verilog. So this is how you can actually implement a 4-bit triple carry adder that we saw at the beginning of this lesson using Verilog. Okay, so now that we have implemented the circuit module we wanted using Verilog, we come to another important part. Now this is about testing the circuit or design block we implemented to see if it works as we want. Now, for example, in our adder module, we want to see whether it actually can add two values given to it and whether it can give the result in the sum output, whether it can assign the addition to the sum output. So for this, we actually apply stimulus, or in simpler terms, we give inputs to the module we built and check the result or the output of the module. So this is how you will be doing testing for a circuit element. So even with real hardware, that is what we are doing. So this in Verilog is typically done by using a block called a stimulus block. This stimulus block can also be written as a separate module in Verilog, and we will see how such a block can be written in Verilog next. And another thing that is important is that this stimulus block is commonly called a test bench. So when we say we want to write a test bench for a module we built, we are referring to this stimulus block that we use to test the functionality of an already implemented module. So if I say we need to write a test bench for this adder, for this subtractor, or for this ALU, we are referring to this stimulus block that we use to test the functionality of a design block we implemented. And now here you can see a block diagram of a stimulus block used to verify the functionality of a 4-bit triple carry adder. So our 4-bit triple carry adder module can be tested with a stimulus block like this. Now inside the stimulus block is shown in this green color. So inside the stimulus block or the test bench, the only thing we do is instantiating the design block, the 4-bit triple carry adder. Here in this example, we instantiate the design block and give inputs to the design block, and we observe the outputs coming out of the same design block. So the things that we are doing inside the stimulus block are instantiating the design block and giving inputs to the design block. Here in this example, we give inputs to A, B, and C in, and we then observe the outputs coming out of the design block. Here in this example, the outputs are S and C out. We observe them and see whether they work as we want. Okay, so here you can see how a stimulus block or a test bench or a test bed can be implemented in Verilog to test the functionality of a module. So specifically here this test bed tests the functionality of the triple carry adder for module we built earlier. Actually the stimulus block is nothing but just another module we define in Verilog. So there's no special thing that you have to use to build a stimulus block. It is just another module defined in Verilog. The main difference you can notice here in a stimulus block is that it does not have any inputs or outputs. That is, its input output ports interface or the ports list is empty, right? So this is because we don't get any inputs from the outside world into the test bench module, or we don't give any outputs to the outside world. So we don't need to have a input outputs ports list. You can of course name the stimulus block with any name you want. Here we have named it as stimulus. So this is just another name given to a module. So you can name it as anything you want. So here in this example, we have named it stimulus. So it's good if you use a sensible name here. Since this is a test bench, you can call it either stimulus or test bench, something like that. So general common sense you have to apply here as well, so that it, like, when you are naming variables, modules, and all that, you all know that you have to put a sensible name, meaningful name. So here it's better if you used something like stimulus or test bench as the name. And inside the test bench module, you can see we have defined two register variables, A and B, each of which are 4 bits in size. Now we use these two variables to give inputs to our adder module, mean two numbers that should get added by the adder module. And you can see here these two inputs have been defined as variables of type reg. So they have been defined as variables of type reg, not wires. So this is because we want to assign values to these variables, and we want them to hold their values until we assign another value to them. So since we are going to assign values to them and change these assigned values, we need to define them as variables of type reg. For the outputs coming out from the adder, we have defined two wires, two variables as variables of type wire, and a wire named S, which is 4 bits in size. This is used to get the sum output of the adder, and then a single bit wire named C out is used to get the final carry out from the adder. Since we are not assigning values to them ourselves, and we only observe the values assigned to them by the adder module, we have to define them as wires. So we define them as just wires because we are not assigning values to them ourselves. The values are going to be assigned by the ripple carry adder module. So the only thing we do here is observing the values that are assigned to them by the adder module. So we have to we define them as just wires because of this reason. And then we do one of the most important tasks done in a test bench, that is instantiating the design block we want to test. Here in this example, we instantiate a ripple carry adder for module, right? You can see here we instantiate a ripple carry adder for module because that is what we want to test here. Anyway, this is also a usual instantiation we have seen before. We earlier saw how a full adder module can be instantiated multiple times to get the behavior of the 4-bit triple carry adder module. And here again, this is a usual instantiation we have seen before. Therefore, you have to first give the module name and then a unique name for the instantiated module. So the unique name we have given to this instantiated module is RCA. So this is the syntax. This is the same syntax you used for a usual instantiation. And then you can connect the reg and wire variables we declared above as the inputs and outputs of the ripple carry adder module. So you can see here AB 0 is see out these things have been connected as inputs and outputs for the triple carry adder 4 module. So another uh, important thing, or maybe something that is new to you, uh, you can notice here that for the carry in input of the adder, we have connected a binary 0 value. Just after A, B inputs, you see here one uh, apostrophe B0. So that is a binary value 0. We have connected uh, a constant 0 value there, and this actually is similar to hardwiring a logic 0 to an input. So when you are doing physical labs, you use for some like for input for some inputs you connect 0 volts directly. You are not going to change that value later. So this we call as hardwiring. So we hardwire a logic 0 or 0 volts to this particular input by using this technique. You can do that. So that is how we make sure that carry in of the adder is always 0. And then the last thing we need to, last and but not the least thing, we need to do is assigning some values to the input variables with time, and then observing the outputs to see whether it works as we want. Now for this, we need to use something called an initial block in Verilog. So this is something new to you all because we have not looked at initial blocks before. Actually, in this course and most other cases, initial blocks are used only inside test benches or stimulus blocks, and they are not typically used inside design blocks such as triple carry adder 4. So you will not be seeing these initial blocks inside design blocks. Only inside stimulus blocks you will see them. And to declare an initial block, you need to use this keyword initial, and everything that happens inside an initial block should be put inside. You should put all that inside the two keywords begin and end. You can see that here in this example. Everything that should happen inside the initial block has to be put inside these two begin and end keywords. Now, inside an initial block, we can define or write things that should happen only once in the order that they should happen. So this is more like sequential programming in C, but there are slight differences as we are dealing with hardware elements in Verilog or HDL. So you will understand them better when you actually start using them. How an initial block can be used in a design, you can in a stimulus block, you will understand them better when you actually start using them. Here is a good starting point where you can get an idea about initial blocks. Uh, so anyway, in this example, inside the initial block, the first thing we do is assigning values to the inputs A and B. We assign 4-bit binary value 1100 to A and binary value 0010 to B. Now for assigning values to A and B, you can see we have used this sign smaller than or equal. So this actually is not an operator used for comparison as it is in other places. In other places like C and in other programming languages, and even in Verilog, when you are doing a condition check, you will use this operator as a comparison, as a comparator used for comparison. But here it is not the case. This operator or the sign smaller than or equal is used to assign a value to a variable or a register here in this to be specific. So this is a special sign used for an assignment called a non-blocking assignment in Verilog. So for now, you can just assume it's just a symbol used to assign a value to a variable. Actually, here in this example, you can use the usual equal sign as well for assigning values to A and B, and it will not make a difference because there are two types of assignments in Verilog called non-blocking assignment and blocking assignment. And for non-blocking assignments, we use this special sign smaller than or equal. And for blocking assignments, we use the equal sign. And the difference between non-blocking and blocking, you don't need to worry about that here at this stage. If we have time, we'll try to look at that as well. But here you can use either this smaller than or equal sign or just equal sign, and it will not make a huge difference. So you can try that equal sign as well and see whether it works properly. So anyway, now we have assigned two values to A and B inputs. Now there's something new done here again. That is this #1 in the code. So this construct is used to wait for a given amount of time before we go and do something else. The time here the amount of time here is measured in terms of simulation time units. There's no specific time unit used like something like nanosecond, picosecond. That is not specified here when you are specifying the time. You just specify the time in terms of simulation time units. So here what we are doing is we have get the need of waiting for one simulation time unit before checking the output. So that is exactly what we are doing with #1. So we wait for one simulation time unit before we go and check the output of the module. So after waiting for one time unit, we try to display the values in signals connected to inputs and outputs of the adder module. For this, we use this display system task. So we already have looked at this display system task. The syntax to use with this display system task also, we have already looked at that in previous lessons. Here we use the uh, displayed system task to print the values in signals A, B, S, and Cout formatted according to the given formatting string. Right? So with this one, you can actually with this test bench. So that is all about this test bench we have written. And with this test bench, what we are trying to do is we assign two values to A and B, and after waiting for one simulation time unit, we display the values in A, B, S, and Cout. So by looking at S and Cout, we can verify whether it did the job of the adder. So with this, we can verify that our adder is working as we want or not. So anyway, finally, this is how you implement a simple digital circuit using hierarchical modeling in Verilog and test it with a test bench. So this actually was a bit lengthy lesson since we went into details of implementation with a real example. So you can try out this example on your own and see how it works. So there are two remaining lessons and they are going to be shorter compared to this one as we'll be looking at fine details about some of the things that we already looked at in this lesson. Again, you should try out the examples I discussed in this lesson, and if you get into any issues, you can use the forum to raise them. So that is about this lesson. See you in the next lesson. Bye.